Hello, welcome to Cloud Clarity. In this channel, we provide in-depth technical content and analysis on topics in the cloud technology space, including public and private clouds, infrastructure layer, and application layer technologies. Let's get started. This is what we just said, and we're going to focus on a number of technologies, and we'll focus a little bit more on open source projects from within the Cloud Native Computing Foundation, the Linux Foundation, and so on. This is a little bit about me. My name is Sanjeev Rampal. I have extensive experience building products and solutions in the cloud and networking spaces. Here is some contact information. Should you choose to get in touch with me, feel free to reach out. With that, let's get into this topic for today. The topic for today is the design and demo for a service load balancer for Kubernetes using eBpf technology. Kubernetes, as you may be aware, has both north-south services and east-west services. And in this demo, we are going to demonstrate a load balancer for north-south services, in particular Kubernetes node port services using eBpf technology. The agenda is as follows. We will do a brief introduction and problem description, describe possible solutions using eBpf to implement this function, describe a little bit more about the option that we choose to implement in this approach, in this solution. And then we'll be providing a demo, which will be most of this particular session. So let's start with the problem we are trying to solve. What is a Kubernetes north-south service, and what specifically is the node port service? So this diagram shows a Kubernetes cluster with a few worker nodes, and you see that there is a service implemented with two pods in the backend providing the implementation of the service. These pods use IP addresses that are private to the cluster. So this service, in order to access the service from outside this cluster, it has to be exported in some manner. And one way to do it is using the node port Kubernetes service. With this approach, the service is made accessible at a particular port, TCP or UDP port, on the IP address of each of the worker nodes of the cluster. So you can see here, this service is available on port 31,000 of the worker nodes. So if two clients, let's say in this case, the blue client and the green client, want to access the service, they can initiate requests to any of the worker nodes at this port, and the infrastructure implementing this service will take care of load balancing these requests to different backends to provide this service, and taking care of everything else, including NAT and stateful operations and connection tracking and so on. So that, in a nutshell, is a Kubernetes node port service. Digging a little bit more generically, we see that sometimes the backend of such a service the pods can be distributed across multiple worker nodes. And it is also possible that a client may choose to initiate a request to one possible worker node, but either there is no backend pod currently on that worker node, or for whatever reason, the infrastructure on that node decides that it is better to serve this request using a pod in another worker node. So in this case, the request from the green client is actually turned around and bounced effectively to the other worker node, where it is then served by this backend pod. We won't focus too much on this sort of data path in today's demo. We'll focus on a data path similar to the blue client, where the request comes in on worker nodes, which do have backend pods to service these requests. So that was briefly the problem. Now, what are possible solutions if we want to implement this via eBpf? And why would we even want to implement this via eBpf? A few different reasons. One is that the current implementation in upstream Kubernetes for the node port service relies on the Linux iptables modules. And iptables is somewhat deprecated. There is no new functionality being added to iptables by the Linux community. So for future functionality, you would be limited if you were to continue to use iptables. And another reason is that eBpf technology has been getting a lot of attention. It allows us the ability to insert programmability into the Linux kernel without writing dedicated kernel modules or updating the Linux kernel directly itself. The development cycle for that is extensive and long. And so eBpf programs provide an ability to create additional programmability and execute it in a sandboxed virtual machine effectively that still is running within the kernel context. So that's one of the reasons why eBpf has been getting attention. And the net benefit is also that one could potentially get more flexibility and potentially higher performance in the data path when using some eBpf functionality in the kernel data path. So those are the reasons why one might want to implement this service using eBpf. And that's what we're choosing to do in this experiment. So even if you've decided to use eBpf, there are actually a few different ways one could use eBpf to implement this functionality. Let's briefly look at 3 of these approaches, right? In approach A1, we could write a complete new data path outside of the kernel for largely. And that does, connection tracking or Conntrack and NAT and load balancing functions in eBpf programs in this parallel data path. And this is an approach used in the Cilium CNI for the Kubernetes service, for the Kubernetes node port service. Approach A2 is to leverage kernel's own Conntrack module and NAT modules and so on, but use eBpf TC and XDP programs based on new and upcoming eBpf functionality to set these up, right? So this approach A2 has more of a reuse of the kernel. And that's the approach we use in this solution. Approach A3 would be to use socket-based load balancing. Also, this would also be a separate data path outside of the current kernel data path. And this is similar. This is an extension of ideas that have been used in projects such as Cilium and others that perform cluster IP services using socket networking implementations of eBpf. So that would be approach A3. More analysis and comparison of these approaches is in a gist that we documented, and the link is provided in the description. So there's benefits of each of these approaches. We are going to look at A2 partly because we wanted to try out these new eBpf capabilities and felt like it would be worthwhile to have an approach which preserves the kernel data path as much as possible and only selectively uses eBpf. So that's what we're going to prototype and demo in this solution. So we talked about TCE and XDP and Conntrack. Let's look at the Linux kernel data path in a little bit more detail to understand how these fit in. So this is a fairly detailed view of the Linux kernel networking data path, and in particular, the net filter data path. Traffic comes in and is on a particular ingress interface. And there are two locations or hook points early in the data path where eBpf programs can be attached, namely the XDP hook and the TC or traffic control hook. There are also hooks at various other points in the data path. For the approach A2, we would be focusing on eBpf capabilities at the XDP and TC hooks. In a normal data path, traffic would go through these stages and then go through the regular kernel net filter data path, starting with the connection tracking module, which is an important module that detects and maintains the state of connections in and out of the system. And that information is then used by subsequent tables and chains within NetFilter to do connection aware and connection state aware, stateful NAT and stateful filtering and so on, stateful firewalling, for example. So when we talked about approaches A1, A2, and A3, in the approach A2, which is what we're prototyping here, we will essentially examine packets early at either the XDP or TC locations. And in the demo, we are looking at it at the TC location, but we could do this at the XDP location as well. And we examine whether this incoming traffic is a new connection or an existing connection. And we do that by looking up this flow, the 5-tuple of the flow, in the connection tracking table. So we look at source IP, source port, destination IP, destination port, and protocol type. And if this packet is belonging to an existing connection that is already being tracked, we let it go back to the kernel and let the kernel handle it. If this is a new packet for a new connection, we then invoke a BPF program to perform a load balancing operation if this packet is destined to a node port service. So if this is coming into the virtual node port service, we maintain a hash table of the different node port services on this cluster and perform a load balancing operation. We pick a backend, a suitable backend to balance this particular new connection to. We determine the appropriate SNAT and DNAT operations that need to happen. And then we program that information into the connection tracking table. So we create a new connection entry for this new connection. This is somewhat like what the IP tables plus NetFilter would have done had IP tables been present. But we mentioned earlier, one of the goals of this solution is to do this without needing IP tables. So that's what we are doing this via the eBpf programs. And what happens then is that once we've created this Conntrack entry, we then let it go through the regular kernel data path. So we talked about reusing the kernel data path where possible. So subsequent packets come in and then they are passed directly to the kernel. And when they look up in the Conntrack table, it's a hash table lookup. And with a single lookup, the additional packets will find the connection tracking entry, as well as the load balancing and NATing information. All that is cached as part of the connection tracking entry. So with a fixed number of operations, the kernel would then be able to just execute the load balancing and NATing that we've set up in eBpf for this connection. Now we can also see why this would potentially have some performance improvement over the iptables approach. If we were to do this with iptables, for the first packet that comes in for new connection, we would need to sequentially walk through all the iptable rules to find the matching node port service. So we would sequentially walk through all the cluster IP services rules and then all the node port rules. And then we would set up the connection tracking table and so on. With eBpf, we are able to do a single lookup in a services table and immediately find all the information needed for NATing and load balancing and setting up Conntrack. So the processing of new connections is much faster and is independent of the number of services, both cluster IP services and node port services, and other IP table rules that are in the net filter framework if we were to use IP tables. So there you see the potential for performance improvement, as well as the fact that we didn't actually need to depend upon IP tables, which, as we said earlier, is a deprecated module in Linux. So that sort of explains what we're doing here. There's a bit more detail here, but hopefully that will also become clearer when we look at the demo. So now let's look at the demo setup. So in this demo setup, we are running a Kubernetes cluster using Kubernetes in Docker. And we have a virtual machine here in which we have this kind cluster. This virtual machine, in fact, is running a custom kernel. The reason for needing this custom kernel is, as we mentioned earlier, we are using new eBpf helpers to manipulate the connection table entries. And these new eBpf capabilities are just getting added to upstream Linux kernel. They are not yet available in the GA Linux kernel and hence also not available in any of the Linux distributions. But they are on track and will soon be available both in upstream Linux, possibly in the 6.1 kernel release, and subsequently in various distributions. So since we wanted to leverage those functions and try them out, we are building this solution with a custom built kernel for now. So we see that this cluster, there's a deployment with a service, a node port service, with two backends, in this case, two pods. Both happen to be running on the single worker node. And we are going to attach a BPF program to the TC hook of the incoming interface on this worker node of the cluster, right? So we mentioned earlier about the TC hooks and so on. This is where we're going to attach the BPF program, perform the connection tracking setup and so on, and the load balancing towards these backends. And then we will be able to access this node port service from an external client. In this case, we will simply use curl or a browser from the underlying machine, and the node port would be forwarded into the kind cluster and into the worker node providing this service. So now let's look at our actual system. So we mentioned earlier that we have a kind cluster. Here we see it. There's cluster 1. And we have set up a deployment for a web server. So let's look at our deployments. So we have an Nginx deployment with 2 backend pods backing up this deployment. The KC command here is an alias for kubectl. So now we want to expose this deployment as a node port service, but we do not want to use iptables. So we want to attach a BPF program to perform this function. And we are going to do that by loading a BPF program. The details of this program are in a GitHub repo that I have provided the link in the description. Let me briefly flash that repo here, but you can look at it later. Let's see. So this is the repo in which all the code for this prototype is available, and feel free to look at it later. So we are going to run this executable on the TC hook of the worker node. So since we are doing this in kind, let's access the worker node through the Docker shell. Now, normally, and eventually, this function would be part of a Kubernetes operator and controller that would be performing this attachment. Because we are using these new and very, very new BPF and functionality, it was not possible to use the current loading functionality in Rust and in Golang to load this BPF program, and hence we are loading it through the shell like this. But eventually, this will be through a Kubernetes controller. So what we do here is, let's see, we can do. So we can launch this BPF program and tell it to attach on ETH0, look for node port 31,000, and balance that to backends 10.1.1.6 and 10.1.1.7, which are the two backend ports, and use the target port 80. So now the BPF program is attached. Now we should be able to access the service from the outside of the cluster. So let's do that. Let's curl to localhost on the underlying machine at port 31,000. And we've set up the port forwarding to go inside the client cluster. And we see that we did get a response from an Nginx backend. We put it in particular, we got it from backend A. If we make another request to the same node port service, this time we got the response from backend B. So clearly we are getting balanced to different backends when accessing this node port service from outside. So the node port service appears to be working. Let's confirm that further by looking into the logs of the actual backends to see the requests coming in and getting load balanced to the backends themselves. So let's look at maybe the logs and one of these Nginx pods. So let's say right here. So we're looking at one of the pods. Let's send in a request. So this request came from backend B, which was probably different from this backend pod. Let's send another request. And we see that that request got load balanced to this particular pod now. We got in the curl get request, and we got the response from backend A. So we keep making requests, and they will get load balanced to the different backend. And all the NATs operation and so on is happening because the external client is not really aware of which particular, it's not really targeting individual backend pods, and all the NAT operations and load balancing operations that are handled transparently under the covers. So let's confirm that we aren't actually doing anything with iptables in order to implement this. And this is actually happening with eBpf programs manipulating the connection tracking table. Let's look at the iptable rules on the kind worker node. So let's go into the worker node again. And let's look at iptables. And in particular, let's look at the NAT tables, because that's where NATing and load balancing is set up. And in standard Kubernetes, when using kube-proxy, kube node ports is the service chain where rules for node port services are added. So we see there are no rules for node port services in iptables and in the NAT table and the NAT table, yes. So we're not using iptables and we're performing this node port load balancing function. Let's also look while we are here at the kube services, which is the chain used for other Kubernetes services. So we see that we do have rules populated. Okay, in this particular system, we do have IP tables for other services, meaning the cluster IP services, and but we do not have any IP table rules for the node port services, which is what we're implementing with eBpf here. We could choose to also implement the cluster IP services with eBpf, and there would be no IP table rules at all. But if we were doing this with IP tables, you can see that the net filter framework would need to walk sequentially through each of these cluster IP services, and then eventually each of the node port services in order to find the matching node port service for an incoming traffic. And that is where IP tables would be less performant than eBpf, because in eBpf, we do a single lookup in a service table, and we immediately get the backend information. We populate that into a connection tracking table, and off we go. And we are still using most of the kernel functionality. We're not replacing it with a parallel data path. So we talked about connection tracking. Let's actually look at the connection tracking table as well. So let's so it appears that the table entries have aged out. So let's send another request here, and we see that there has been a entry created for the flow for the connection to port 31,000. So you see that this connection tracking table entry is for traffic from this source, which is the external IP address. Destination is one of the worker node IP addresses, which in this case is 1803. The source port is from the client, and the destination port is our node port. And we are also setting up the NAT mapping, the load balancing, and all the connection tracking for the reverse traffic. So this particular program has chosen to load balance this request to the port with IP 10116, which is where the reverse traffic would be sourced from. And there's more detail here about how the connection tracking works. But essentially, this is an assured connection. It has seen traffic in both directions. And that's what we've done here. If we send another curl request and look for the connection tracking table again, this time we see two connection tracking entries, one getting load balanced to the port at 10116 and the other getting load balanced to 10117. So we see that we are creating entries in the kernel connection tracking table in order to implement this function. We don't have IP tables, or we're not using IP tables for node port services. And we were able to implement this using these new eBpf capabilities. And now we haven't really touched the kernel, the core kernel. We're still leveraging the kernel data path as much as we can. We're not trying to reduplicate a major part of the kernel data path in an eBpf program. So that's the benefit of this solution. There's pros and cons of each of these approaches. More details are in the links that we provided. So that was really the demo. Hopefully that was useful. That gave you some insight into different ways of doing Kubernetes load balancing and the insights into how to do it with eBpf with various approaches, and how the connection tracking and NAT and so on works. Thanks for watching. We should have more such topics in future. Feel free to reach out, provide comments, ask questions. Happy to discuss. Thank you, and see you later.